This is chapter 4 where we discuss bending. This is the 17th session overall and the first session related to bending. Here we introduce bending, mention the types of supports and beams we will encounter, and start the discussion on bending moment and shear force diagrams. This is the first session in bending out of 20 sessions, as we can see. Earlier we have discussed stress and strain, which are basic considerations. We have also discussed loading types such as axial loads and torsion. Now we are discussing bending. Here we will give a brief introduction to the topics we'll discuss in this chapter. At the end of chapter 2, we gave a general idea of the way we will deal with different types of loadings. So we mentioned that we will deal with different types of loads in the same manner that we dealt with axial loads. Till now, we have dealt with bars subjected to axial forces and circular bars subjected to torque. Here we will deal with beams subjected to transverse forces and hence moment and shear. So this is a prismatic beam supported as shown, and the transverse load is applied on the axis of symmetry. For most of the chapter, we'll consider loads applied on the axis of symmetry. Only in the end of the chapter, we'll consider unsymmetrical loading. We'll consider that the beams are sufficiently laterally constrained. Beams, like columns, can fail by buckling. Hence, sufficient lateral constraint needs to be there to prevent buckling and collapse. Initially, we'll discuss types of supports, types of loads, and beams. A wholesome discussion will be given compared to brief mentions earlier. We have earlier mentioned about the method of sections, which is used to find internal forces. We have found internal forces in bars subjected to axial loads and circular bars subjected to torque. We'll do the same thing with beams. In bars subjected to axial force and circular bars subjected to torque, we had to find the internal forces only in few sections. This is because axial forces and torques in bars and circular bars subjected to torque are constant for large portions of these bars. In contrast, as earlier mentioned, shear force and bending moment often vary throughout the length of the beam. So the internal forces in beams are often given by shear force and bending moment diagrams. We will develop shear force and bending moment diagrams for different types of loads acting on beams. In the case of torque, we found out the variation of strain on a perpendicular section using heuristic arguments. Similarly with beams, we'll find out strains based on heuristic arguments. Like in the case of torque, we'll use this strain variation and Hooke's law to find out the variation of stress on a perpendicular section. In the case of torque, the torsion formula related the internal torque to the stresses acting on the section. In the case of a beam subjected to load on the axis of symmetry, we'll find out a relation between the internal moment and the stresses acting on a perpendicular section. The corresponding formula is known as the flexure formula. At the end of the chapter, we'll also deal with stresses acting on sections subjected to unsymmetric bending. For most of the chapter, we'll deal with straight beams. Only in the end, we deal with out beams. In this chapter, we deal with shear forces only, but not with shear stresses. We'll deal with shear stresses in a different chapter. Here we discuss different types of supports. So we discuss roller support and link. Then we discuss pin support and then fixed support. A roller can only react with a force perpendicular to its tangent on the surface. A roller support is used for a downward load, so it will provide an upward reaction, or an upward load where you can provide a downward reaction. It can also be used in a beam that is inclined with a transverse force, and the roller support will provide a reaction perpendicular to the axis of the beam. Here we see a link which can provide a support to a axial tensile force or compressive force. Thus, it can withstand a push or a pull in the axial direction. A link can provide a reaction to a force for which the vertical to horizontal ratio is fixed. Similarly, a roller supporting an inclined plane with transverse load has the vertical to horizontal directions fixed. A roller is normally depicted in literature in this manner, and a link is depicted as shown. Here we have a pin support. A pin support can withstand any ratio of vertical to horizontal forces, unlike the link or the roller support. In a link, the reaction has to be in a particular direction, while in a pin, the reaction can be in an infinite direction. A pin support is depicted normally as shown here. A pin support cannot withstand a moment, but a fixed support can withstand a moment. A fixed support can also withstand vertical and horizontal forces of any ratio. With a fixed support, if the beam is of concrete, then it is built in the wall, and a steel beam may be welded to the wall. As we can see, a pin support, a beam can rotate, while with a fixed support, the beam cannot rotate. In a pin support, there's no resistance to the beam rotating, while in a fixed support, the wall will provide a counter moment if there's a moment acting to rotate the beam. The wall also counters with vertical and horizontal reactions to any vertical and horizontal force due to the beam. A fixed support is typically depicted as shown here. So there's an internal moment and internal forces in the vertical and the horizontal directions. Here we discuss classification of beams as well as types of loads. So a beam can be a simply supported beam, a cantilever beam, overhanging beam, a fixed beam, or a continuous beam. Among these, fixed beam and continuous beam are statically indeterminate, and we will not discuss these two types of beams at the present. Here, AB is a simply supported beam. It has a hinged support at one end and a roller support at the other end. If there are no horizontal forces acting on this beam, then there are two unknowns at the hinge and at the roller support. There are also two equations of statics. We can consider moment about a point, say A, and summation of vertical forces is equal to 0. Or we can consider moment about 2 points, A and B. Therefore, a simply supported beam is statically determinate. The load can be a point load, say a 30 kN load acting at a point in the beam. It can be an uniformly distributed load, which say can have a magnitude of 5 kN per meter. It does not vary from one end to the other, and hence the prefix uniformly distributed. This is a triangular distributed load. It can have, say, a magnitude of 70 kN meter at A, 30 kN meter somewhere in intermediate between A and B, and 0 at B. There can be other forms of distribution, such as a parabolic distribution of load. This is a case where a moment acts on a simply supported beam. Loads acting on simply supported beam may be combinations, so we can have a point load and a uniformly distributed load acting at the same time. We can have any other combinations also. A cantilever beam has one side fixed and another side free. Here also we consider that there are no forces in the horizontal direction. It has two unknowns, the moment and the reaction at the fixed end. There are also two equations of statics we can use, such as summation Fy is equal to 0 and moment about a point, say B. We can also use moment about any 2 points. With two unknowns and two equations, a cantilever beam is statically determinate. A overhanging beam is similar to a simply supported beam. However, it has overhangs either on both sides or on one side, and these overhangs can carry loads. Without any horizontal forces, here again there are two unknowns and there are two equations. So a overhanging beam is also statically determinate. Here we have a fixed beam. Again, we consider that there are no horizontal forces. This beam is fixed at both ends. So it has two unknowns at both ends. That is four unknowns in total. There are two equations of statics that can be used. This makes the fixed beam statically indeterminate. A continuous beam has a pinned support and more than one roller support. Considering there are no horizontal forces, there are vertical forces that are unknown. So a continuous beam will have three or more unknown vertical forces. So a continuous beam is also statically indeterminate. Here we discuss the method of sections and internal forces in beams. We have earlier discussed that we find out the external reactions first using the equation of statics. After we have found out the external reactions, we use the method of sections to find out the internal forces. Here we will deal with only statically determinate structures. So let us consider this beam. It is subjected to a point load and a uniformly distributed load. By taking moments about point A and point B, we can find out the reactions RA and RB. We then take a section CC as shown. As discussed earlier, if the whole beam is in equilibrium, then a portion of the beam will also be in equilibrium. So the portion left of CC will be in equilibrium. Consider that for equilibrium, at this section, there needs to be a downward vertical force and an anti-clockwise moment as shown. So this left portion is in equilibrium under the reaction, the point load, the uniformly distributed load, and the internal forces, which is a vertical force acting downwards and an anti-clockwise moment acting on the section CC. If we were to consider the portion right of CC, then again considering equilibrium, we'll find that the vertical force acting on the section CC will be upwards, and the moment acting on the section CC would be clockwise. The downward force here and the upward force here form an action-reaction pair, and the moment acting on the left section and the moment acting on the right section form again an action-reaction pair. As we know, action-reaction forces act on different bodies. So this force acts on the left part and this force acts on the right part. Similarly with the moments. Also, the downward force in the left portion is due to the right portion, and this moment, that is anti-clockwise, is also due to the right portion. Similarly, the internal forces in the right portion are due to the left portion, the beam. Now let us look at the direction of shear forces. We can see here that shear forces form an action-reaction pair. So they always occur in twos. So the shear force, if it is downward on the left side, must be upward on the right side. So if we say that the shear force is downward on the left side, we are automatically telling about the direction of the shear force on the right side. If we cut a beam and we find that on the left side the force is acting downwards and on the right side it is acting upwards, we consider the shear force as positive. So here we have two big beam segments, and on the left side we have a downward force, and on the right side an upward force, and this is considered as positive. If the combination is oppositely directed, then the shear force is considered to be negative. The sign can also be denoted in this manner, where on the right, if the force is downwards, as shown here, force is positive, and on the left, if the force is upwards, as shown here, then the force is positive. We can consider an elemental portion such as this here on the left side and here on the right side. Then the forces on this element will be the same as the forces here, and the forces on this element will be similar to the forces here. That is a downward force on the right face and an upward force on the left face. These forces tend to rotate the element clockwise. So both in this case and in this case, the shear forces will tend to rotate the element clockwise and therefore is positive. Such a sign convention, which depends upon deformation, is called a deformation sign convention. An element in a bar subjected to tensile forces extending also follows deformation sign convention. If the combination of shear forces tend to rotate the element anti-clockwise, then the shear force combination is considered as negative, as shown here. Consider sign of bending moments. We took a section CC and found that there's an action-reaction pair acting at the section of shear forces and bending moment. Like shear forces, if the direction of the bending moment acting on the left section is known, the direction on the right side is automatically known. So we assign the signs of both the bending moment at the same time, not to one moment. Here we have the bending moment on the left side as anti-clockwise and the bending moment on the right side as clockwise. This combination is considered to be positive. So here we have two beam segments and the direction is the same as here and is considered positive. The signs can also be given using this elemental portion. We see that the direction of the moment here has the same direction as the moment here, and the direction of the moment on the right side has the same direction here. So these two elements overall, considering both the left and right side, will be subjected to the same moments as this element and therefore are subject to positive moments. The sign can be understood using an extended segment as shown here and subjected to the same moments as this elemental portion. Then the bottom layer here has become convex and the top layer has become concave. The way this segment is deformed will consider that it will hold water. So such a deformation is considered positive. So here again we are following a deformation sign convention. Here, based on deformation, we give the sign. Now consider this element which has been subjected to a negative bending moment. This is an extended beam segment subjected to the same moments, and we can see that the bottom layer has become concave, the top layer is convex. The deformation here can be considered to shed water as opposite from the earlier case. With this type of deformation, the upper fibers in this beam would decrease in length, while the lower fibers would increase in length. With negative moment, it is the opposite. So the lower fibers will decrease in length. We have already chosen a sign convention. So we have assigned the direction of positive shear force and positive bending moment. Before we start looking at bending moment and shear force diagrams, we need to ascertain the direction of the force and moment, say taken from the left side, which we will consider as positive, so that we match the sign convention. Now this is the case we had earlier taken, and here we'll consider the section 2.2. Let us consider a small element as shown here alongside the section 2.2. Depending upon the forces and the moments acting on this element, we will ascertain whether section 2.2 is subjected to positive shear force or negative shear force or positive or negative bending moment. Thus, the element will help us ascertain the sign of shear force and bending moment. At this stage, we do not know the forces and do not know the direction of shear force and bending moment that will act on section 2.2. So here we have taken 2A and 2B where the shear force and bending moment are positive, and we have taken 2C and 2D where the shear force and bending moment are negative. Now from the left, we'll consider forces acting upwards as positive. There are three forces acting here, that is Ra, this point load, and the resultant of this UDL. If the numerical value of Ra is higher, then the sum of the point load and the resultant of this uniformly distributed load, then the value we'll get at section 2.2 is positive. Now let us see if this matches with the sign convention. So if Ra is greater than these two, then on the left side of this element, there would be an upward force as shown here. On the right side of the element, there will be a downward force. This matches with the positive direction of shear force we have taken. Now consider the case where this point load plus the resultant of this uniformly distributed load is greater than Ra. Then since upward is positive, the value that we'll get of shear force at section 2.2 is negative. If we consider this element, then since these two forces add up to a larger value than Ra, on the left side we'll get a force acting downwards. For equilibrium, on the right side we'll get a force acting upwards. So the negative shear force value that we have got matches with our sign convention. So we have established that considering forces upward to be positive from the left side matches with our sign convention for shear force. Now let us look at bending moment. From the left, we consider clockwise moment as positive. In this figure, we have taken the moment due to Ra on section 2.2 to be greater than the moment due to this point load and the resultant of this uniformly distributed load. So the net moment acts as shown. For equilibrium, there will be an anti-clockwise moment on the other side of the element. Since we have taken clockwise as positive, the net moment numerically we'll get here is positive, and it matches with our positive sign convention. In this diagram, we have taken the moment due to this point load and the resultant of the uniformly distributed load to be greater than the moment due to Ra. So the net moment is anti-clockwise and negative. The net moment is given here, and on the other side there must be a clockwise moment for equilibrium. So the negative moment here matches with our sign convention. So on the whole, we can say that if we take clockwise moment from the left hand side as positive, then the values that we'll get will match our sign convention. If we consider from the right side, then unlike what we have ascertained from the left side, a downward force is considered as positive since it matches with this sign convention. Also, an anti-clockwise moment needs to be taken as positive to match with our sign convention. Shear force and bending moment diagrams give the variation of shear force and bending moment at perpendicular sections all along the beam. We earlier looked at internal forces in bars subjected to axial loads and circular bars subjected to torque. In such cases, only one or two values were sufficient often to give the axial force or torque throughout the bar. Let us consider this bar to which a load P1 and P2 has been applied. Then from equilibrium, there must be a force P1 minus P2 acting at C. The whole bar ABC has only two different axial forces. If we take a section perpendicular to the axis between A and B, we'll find that the internal force is P1. If we take a perpendicular section between B and C, then we will find that the internal force is P1 minus P2. Bending moment and shear force are also internal forces in beams, but they often vary continuously throughout the beam. Now consider this beam with the loading as shown. There's an uniformly distributed between D and B and a uniformly distributed load between A and C, and there's a point load acting at C. To start with, we can take moment about B and find out Ra, and take moment about A and find out Rb. To give the shear force and the bending moment diagram of the beam, we'll take three sections, 1, 1, 2, 2, and 3, 3 as shown. Sections are taken where the pattern of loading does not change. We take a section 1, 1 at an arbitrary distance x from A and find out the variation of shear force and bending moment between A and C using reasoning. We'll similarly take a section 2-2 at an arbitrary distance x from A and find out the shear force and bending moment between C and B. We'll next take a section 3-3 and find out SF and BM between B and B. So this is the general procedure used to find out shear force and bending moment diagrams in a beam.